Hi, my name is Josh Robbins, and today I will be presenting to you some work that my co-authors and I have done on energy-aware predictive motion planning for autonomous aerial vehicles using a hybrid zonotope constraint representation. So there are several emerging uncrewed aerial system or UAS applications under development. These include air taxis, air ambulances, and package delivery drones. In this 2018 market study that we're showing here on the slide, it specifically calls out energy usage, noise, and weather as key technical challenges for these proposed UAS systems. We believe that these challenges can be addressed in part by developing autonomous planning algorithms that account for the inherent coupling between energy and motion dynamics for aerial vehicles. So as an illustrative example, on the left side of the slide, we are depicting a high-level energy-aware mission planning algorithm. The idea here would be that there's a drone shown at the bottom of the graphic, which must navigate to a hospital shown at the top of the graphic in order to make some emergency medical delivery, for example. The energy-aware mission planner would specify several waysets in this case, which are generalizations of waypoints and are depicted here as pink polytopes. These waysets would specify energy requirements in addition to position requirements. So on the right side of this slide is a depiction of an energy-aware motion planning algorithm. And for energy-aware motion planning, the goal would be, in this case, to find a trajectory of the system that navigates the drone to the wayset and ensures that both the terminal position and energy constraints are met. So in general, this is a non-convex problem as the drone may have to navigate around obstacles in the environment. And this may be further complicated by the presence of quiet areas, which in this graphic are depicted as the red region. And these may, for instance, carry some constraints on engine power usage. So we believe that these energy-aware planning algorithms could be an important part of addressing important technical challenges for emerging UAS applications, as they can plan system trajectories that reason about energy usage and noise restrictions, which are both technical challenges that were called out on the previous slide. And they additionally provide a framework for online replanning, which could add robustness to environmental disturbances such as wind. Most of the work on energy-aware planning for UAS so far has focused on mission-level planning, which corresponds to the graphic on the left side of the slide on the previous slide. And that is what most of the references in the top left third of this Venn diagram correspond to. There's additionally been some work on incorporating energy constraints into predictive motion control formulations, and that's what the references in the top right third of the Venn diagram correspond to. The papers in the top center include energy constraints and MPC motion control formulations for UAS, and our work is along these lines as well, but in contrast, we use a mixed integer motion planning formulation. Mixed integer approaches to motion planning have become more popular in recent years, in large part due to computational advances. A challenge with mixed integer approaches is that they tend to be very computationally expensive. A key advantage to these approaches, however, is their expressiveness, as they can model non-convex and disjoint constraints. So our work contributes an approach to mixed integer energy-aware motion planning for UAS. Our contributions include a reduced order model for energy-aware motion planning, efficient hybrid zonotope and constrained zonotope constraint representations, and a mixed integer energy-aware motion planner. So the second and third contributions here build upon some of our prior work for mixed integer motion planning with a hybrid zonotope constraint representation. This slide presents some quick background on constrained zonotopes and hybrid zonotopes, which are advanced set representations most often used in reachability analysis, and which we use to represent constraint sets in our motion planner. So constrained zonotopes are defined by this equation on the left side of the slide, and they represent convex polytopes. Hybrid zonotopes extend constrained zonotopes by including binary variables, and they're represented by this equation on the right side of the slide. And additionally, hybrid zonotopes can be formulated to be sharp, which means that if the binary variables are relaxed to continuous variables, the resulting set, which in this case would be a constrained zonotope, is the convex hull of the original hybrid zonotope. And this property is important for mixed integer optimization, as typically this will result in a branch and bound based algorithm convergent in fewer iterations. The first of our contributions for energy-aware motion planning for UAS was to develop a reduced order model. So we sought a model that has linear dynamics, which is required by the motion planner we developed in prior work. And additionally, we needed a model which is globally valid since we were doing non-convex optimization. And of course, we needed this model to couple the motion dynamics to the energy dynamics. For the motion dynamics, we used a unicycle model, which is a commonly used reduced order model for motion planning, and transformed it into a constrained linear double integrator model by exploiting the differential flatness property of the unicycle model. For the energy dynamics, we used a simple linear hybrid electric power plant model, where a battery and engine can both be used to provide power to a motor, and power can flow to or from the battery to allow for battery charging. To couple the energy and motion dynamics to each other, we used a conservative linear approximation of a quasi-steady power and velocity relationship. So that's what's depicted on the left side of the slide here. So we have a conservative linear fit to this cubic curve here. And using this linear approximation, we get coupled constraints on the velocity components, c dot and eta dot, and the battery and engine power states. So specifically here, we would say that the state vector must belong to the set ZCX, which is a constrained zonotope in our case. So we found an efficient identity for this constrained zonotope state constraint set, which is shown on the left side of the slide here. This set has 7 generators and 3 constraints. In contrast, if we were to build this set from a half-space representation or hrep polytope description, which would be a more typical way to go about building this sort of constraint set, the resulting constrained zonotope would have 13 generators and 9 constraints, so it'd be more complex. And then we're showing what this constrained zonotope looks like in the figure on the right side of the slide here. So these are projections of the 4-dimensional set here. So the green projection corresponds to the case of minimum engine power, and the red projection corresponds to the case of maximum engine power. The X and Y components of the figure are the velocity components, and then the Z axis of the figure is the battery power. So when there's more total power available, the vehicle is able to go faster, and that's how we're coupling the motion dynamics to the energy dynamics. We additionally represent keep-out area constraints and noise-restricted area constraints using a hybrid zonotope representation. So for the noise-restricted area constraints, we assume that in the case of a hybrid electric UAS, the noise restrictions translate to restrictions on engine power when the vehicle is operating in these areas. And we couple these engine power constraints to a map of the environment by adding a third dimension, which we can see in this figure on the right here. So the X and Y axes of this figure are X and Y position coordinates, and then the Z axis is engine power. So when operating in the red noise restricted areas, there's significantly less engine power available to the vehicle than when operating in the blue free space areas. So we build this constraint from a vertex representation or VREP description, and we use a VREP to hybrid zonotope conversion, which can be found in reference 1 at the bottom of the slide here. And a result from our prior work shows that hybrid zonotopes constructed this way are sharp, which again means that their convex relaxation is equal to their convex hull. And we exploit this property for efficient optimization in our motion planner. So we formulate the energy-aware motion planning problem as a mixed integer MPC optimization problem. We're using a quadratic objective, LTI dynamics, constrained zonotope state and input constraints, hybrid zonotope constraints on an output vector y, which in this case is just the position states and the engine power, and is what we showed on the previous slide. And additionally, we have optional fixed costs, which are associated with being in certain regions of the map. And we could use this, for instance, to disincentivize the UAS entering certain areas. Okay, so now getting into some simulation results. We first applied this energy-aware motion planner to a hybrid electric UAS model, which must adhere to engine power constraints when operating in noise-restricted areas. So looking at this graphic on the left, the goal of the motion planner is to navigate the vehicle around the keep-out areas, which are here depicted in gray, and to ensure that the engine power constraints are satisfied while the vehicle is operating in the red noise-restricted areas. In the figure in the center of the slide, we have the energy states associated with this optimal motion plan. Where the dots are red, that corresponds to time steps where the vehicle is inside a noise-restricted area. And we can see here at the bottom that the motion plan is adhering to the engine power limits while the vehicle is inside a noise-restricted area. And we can see on the top that the motion planner has taken preemptive action to charge the battery in anticipation of entering a noise-restricted area. It's making sure that it has enough battery energy available to get the vehicle through the noise-restricted area while on limited engine power. So using our proposed problem formulation and the motion planner that we've developed in prior work, the optimization time for this example was 0.86 seconds. And for comparison, an equivalent formulation using a more conventional constraint representation and using the state-of-the-art commercial solver Gurobi solved in about 3.2 times as much time. We also applied our energy-aware motion planner to an example with an electric package delivery drone. So the idea here is that the motion planner must find a trajectory that avoids obstacles in the environment, again here depicted in gray, and achieves the way set at the end of the horizon, which is here depicted in purple. So this way set in this case specifies both position constraints and a constraint that the battery state of charge must be above 0.9 when the vehicle enters the way set. And additionally, in this example, we have some regions of the map that have elevated cost associated with them. So the idea is that we want to disincentivize the UAS flying too close to an obstacle in this example. So here the motion planner is able to find a trajectory which both avoids the obstacles and the elevated cost regions while adhering to the way set constraint at the end of the horizon. So you can see that the state of charge here is above 0.9 at the end of the horizon. And the optimization time in this case using our approach was about 0.96 seconds. So in this example, it's the same as the previous example, but we've increased the terminal state of charge constraint from 0.9 to 0.93. And in order to meet this constraint, the motion planner had to select an alternate trajectory that drove the vehicle through one of the elevated cost regions. So this shows some of the utility of combining the energy states and the motion states in a single optimization. And the optimization time for this example was 0.83 seconds. So in summary, we presented an efficient mixed integer energy-aware motion planner for UAS and applied it to example problems in advanced air mobility. The motion planning approach we developed leveraged a reduced order model for energy-aware planning and efficient constrained zonotope and hybrid zonotope constraint representations. So that's my talk, and thank you for your attention.